assume quite safely that most of you are running EIGRP in your networks. So please let me ask you at this moment, every one of you, raise your hand if you believe troubleshooting EIGRP is easy. Wonderful. Thank you. I feel your pain. I feel your pain. Let me tell you my story with EIGRP. Before I joined Cisco, I used to be a university teacher back in Slovakia. And as a part of our networking curricula, we had CCNA and CCNP courses with the trainings, and obviously we did also EIGRP trainings. And now, when it came to configuring, deploying, the guides for that have been all across the place. But when it came to understanding what's inside the hood, how they tick, that information was nowhere to be found. And for me, that was a challenge. I wanted to know what's inside, what's happening, how does the EIGRP work, because, of all those white papers, they painted EIGRP as the best thing since sliced bread, which, by the way, it is. But I had no way of telling there. So over time, as we played with the EIGRP, and the students are wonderful to test all impossible things with the EIGRP, finding out all those tiny jewels of information across the internet that spelled something about what's EIGRP. And then finally meeting a couple of people who are the grandfathers of EIGRP in iOS, Donnie Savage, Don Slice, Steve Moore, Russ White, that allowed me to see the mosaic of the wonderful mechanism that EIGRP is, and I ended up having EIGRP as my favorite distance vector protocol. By the way, my favorite link state is IS, just in case somebody wondered. So I learned EIGRP in a kind of hard way, but in a kind of a rewarding way, and I would like to share some of that with you now. Our agenda is quite packed. I would like to talk a little about the tools we have available to see into what's EIGRP doing. Then I would like to split EIGRP into its functional areas and talk about what can go wrong in them individually. So we have the adjacencies, we have the initial synchronization between neighbors, we then have best path selection, installation of the routes into routing table, and disseminating that information, and always keeping up to date. And we'll also look at some of the added features that have been added into EIGRP in some of the last years. And hopefully we'll end up in time, because afterwards there are a couple of very nice parties this evening. I love questions. Please keep them coming. Just raise your hand and shout. I might postpone some of those questions after the session if we seem like we're running out of time. And also, as you know, you can always pose your questions into the Spark I'm Sorry WebEx Teams, and I'll try to do my best to answer them. This being said, let's go on with it. When it comes to troubleshooting, and I'm just talking now about troubleshooting any system, not just EIGRP, when do you start to troubleshoot people? When there's a problem. And the problem is typically, I see the bloody thing doing something, and it's not what I expected it to do, right? When you do it more formally, we can say that the troubleshooting starts when we see that our idea about how a system works differs from what the system is really doing. And so the troubleshooting can be seen as a focused effort to make that gap between what the system does and what we want it to do as small as possible. Typically, we fix the system. But with systems, as EIGRP is, and EIGRP is based on, well, very clever ideas, but non-obvious ideas, it's sometimes also it's the case that we actually fix our own understanding. And as you know, there has been a lot of imprecise information circulating around the internet about what's going in EIGRP over the time. Hopefully, we'll be able to dispel some of those inaccuracies now. So, what do we need to do a good troubleshooting job? First of all, we need to understand how the system really works. Hopefully, I'm going to help something here. Then we need tools to see what the system is actually doing, to understand what it's doing and if it's going astray. And we need some kind of focused and concerted effort just to make sure that our work isn't diluted into many areas at the same time. If we split EIGRP into functional areas, that's going to help, because that's how those pieces fit together, and this is how we can make a structured approach. And splitting it is essentially in the way we are going to also have this session organized.
adjacencies, synchronization, best path selection, afterwards keeping up to date, so disseminating the information, reacting to events, and keeping this all the time so that we always have loop-free and shortest paths. And what tools do we have to look into the system? Well, show commands, obviously, they are our most used window into what EIGRP is doing. We have event logs or event histories. If things start going really bad, we have packet captures. And if things are very wrong, then you feel kind of comfortable, otherwise not, using debugs. Let's have a look at a couple of them. For my information, please raise your hand who is running EIGRP on iOS or iOS XE. Most of you. Thank you. So you know very well that on iOS and iOS XE, we had a classical mode of configuring EIGRP with the numbers, router EIGRP and a number of the autonomous system. And later, a named mode came in that resembles the way we configure BGP. Consequently, we also have two sets of show commands. One of them is aligned with the named mode. The other one is aligned with the numbered mode. They are largely equivalent for what we need here. The slide deck here will be using the numbered version because they are shorter. But otherwise, they are equivalent. Regarding looking into packets and the communication of the routers between themselves, on iOS and iOS XE platforms, we can use what we call embedded packet capture. Just very briefly, embedded packet capture is your friend when you need to see what packets your router is sending and what it's receiving. Tell me. Oh, I'm sorry. I was kind of mad. Thank you. Regarding the embedded packet capture, it's a tool that allows you to store the packets that your router is receiving and sending into a memory buffer and then dump them into a file to be analyzed offline using Wireshark. Useful tool. And if you need to do debugs on iOS and iOS XE platforms, you know just as well as I do, these are powerful things. They can tell you very much, but they can also tax your CPU very much. So if you need to do them, make sure you deactivate the outputs console and let your router or switch log the debug outputs into either a log file or into the buffered log and read them from there. There is one neglected feature on iOS and iOS XE with logging, and this is called the event log or event history. The idea is that this is a mechanism that runs in background without any noticeable CPU impact and logs every event that was processed by EIGRP. The amount of logging is very close to what we see in debugs, and this allows you to see the things in temporal perspective. You can go back in time and see what was happening. It has been a hidden command in iOS 12.1, 12.2. Afterwards, we have made this command visible. So you can see that even if you're running an old iOS, hopefully you're not. By default, we log about 500 lines of events. If that's necessary to be tuned, you can do that using the EIGRP event log size command. And displaying this log can be done later with the show command. It's also able to clear it. This is your friend because, once again, the detailedness of information which is there is close to debugs and can help you very much to see what was happening some time in the past. Regarding NXOS, and again, my question is, who is running EIGRP on NXOS? Good, thank you. You know that the show commands are essentially the same, so no surprise here. In addition, NXOS has event histories as a matter of fact, not just for EIGRP, but also for other systems. So what do we have as an added feature for iOS, those event logs? They are there in the NXOS by default. Another great tool in NXOS is the Ethanalyzer, which is an improved version of embedded packet capture. Essentially, that one is a T-Shark, the text version of Wireshark. Allows you to see and dissect the supervisor going and supervisor leaving traffic from your Nexus switch in real time. Be mindful that, of course, this is extra processing on your supervisor, so the CPU might be slightly elevated, but it's still safe. If you happen to need debugs on NXOS platform, you can do them. Typically, they're not needed. Just make sure you're using the debug log file to make them, again, go into a file and not somewhere onto the console. All right. These will be the tools I will be referring to later in the presentation. This being said, let's check the first area of EIGRP, which is named the Neighbor Adjacency Initial Sync Issues. Regarding EIGRP organizes several tables. Those tables would be the interface table, which lists all interfaces that are enabled in EIGRP and which are not passive. This is important. Second table is the neighbor table. These are all the neighbors that have been recognized over the interfaces and being labeled as known and ready for exchange of routing information. And third, we have the topology table, which is EIGRP's playground regarding all information about possible destinations. These three tables are crucial because they also form a logical sequence. If you don't have an interface to a neighbor, you cannot have a neighborship with him. If I do have an interface to a neighbor, but I don't see that neighbor in my neighbor table, I cannot learn routes from him. And if even I have a neighbor, but I don't see a route from him in the topology table, I cannot install it in the routing table because I don't know it even exists. So these are your friends, and these will be very helpful to look at. Now, as you know, EIGRP can only accept information from neighbors it knows. This is essentially done to make sure that EIGRP is an event-driven protocol as opposed to RIP, which is a time-driven protocol. We need to maintain adjacencies. Neighbors can be discovered either dynamically using multicasts or they can be configured statically. Either way, they need to meet a several set of parameters to become neighbors. That's my question for you. What parameters in configuration need to be identical for two neighbors to become EIGRP neighbors? Just shout. AS number, perfect. K values, wonderful. Authentication, if you're using it, it has to be identical. And one more thing. Shared link that translates to the common subnet. Perfect, you got it, exactly right. We need to use the same process number, sometimes called also the EIGRP AS number. We need to be on the common subnet, connected with an interface that is enabled in EIGRP and is not passive. Use the same K values and use the same authentication. Well, these are the necessary conditions. Sometimes things can still go wrong, but this has to be met. Regarding the way EIGRP builds up adjacencies, I'd like to dwell a little on this slide. The key takeaway from this slide is that when two routers establish an adjacency between them, the process is very similar to how TCP establishes a session between a client and a server. You know the SYN-ACK communication. A very similar thing is going to happen in EIGRP. Let me show you. Let's say R1 sends out a hello packet. That hello packet is going to be received by
Motorola Edge 50 Pro has redefined flagship smartphone
and put the R1 there. It will put R1 into a state we call the pending state. The pending state does not allow us to exchange routing information, but we know that the neighbor is there and passes those elementary configuration parameters. And also we wait for two events from R1. Waiting for init means that we expect R1 to send us an initial update packet, which is empty, no routing information there, which has an init flag set, meaning I'm starting over. That's the waiting for init. It's like TCP SYN. Then, when we, ourselves, R2, send our own update packet to R1, we expect R1 to acknowledge it. And that's the waiting for init egg. The init egg is something like SYN-ACK in TCP. So let's see what's going to happen. R2 is going to expedite its own hello to allow R1 to discover R2 just as quickly. And R1 is going to do the very same thing. We're going to create a new entry table, neighbor table, put R2 into the pending state, and wait for init and init egg. And now say R2 starts with this null update. There's no routes here. It's just an empty null update. We have the init flag set here, and R2 tells R1 its sequence number. R1 is partially happy because it already received the init. So what's going to do is send back its own null update with the init flag set as well, but also includes the acknowledgement for the packet from R2. R2 is now perfectly happy because it both received the null update from R1, which had the init flag set, and that update also contained the acknowledgement for R2's own update. So R2 now goes fully up, and says, okay, R1 can hear me. All's good. R2 just now acknowledges this information, sends back an acknowledgement to R1, and now R1 is fully happy because it received the init ACK, and so it puts R2 into the full state. Now what happens is just the exchange of the topology tables between these two neighbors. So once again, if we talk about this section here, null update with init, null update with init, and acknowledgement here, this is really like TCP SYN ACK, TCP ACK. This is how it works in EIGRP. Now, what can go wrong in this process? Let's first see the typical output of EIGRP when we check the neighbors. Everybody knows this output, and what information about what's possibly going wrong can we learn from here? Okay, the whole time you know yourself. This is the time we wait for the neighbor to send us some EIGRP packet. If it's not there, we just declare the neighbor dead. Any valid EIGRP packet is going to reset this timer, not just hello, any valid packet. The uptime is self-explanatory. I'm not going to talk about it. Smooth uptime time, this is something interesting. The smooth uptime time is an estimate of how long does it take when I send a reliable packet to the neighbor and the neighbor acknowledges that it got the packet. By the way, when I say reliable packet, what is a reliable packet for EIGRP? What does it mean?
Which one? Unicast could be, but we also have reliable multicast in EIGRP. It has to be acknowledged. And which packets in EIGRP have to be acknowledged? Updates, perfect. Queries and replies. These are the reliable packets. Updates, queries, replies. So I can only update this column here, the value here, if I send a reliable packet to my neighbor. Otherwise, that value stays at the normal situation, the normal value, the last one that was there. And the reliable packets would only be sent if there's actually something going on in your network, right? Because if it's stable, we don't send updates or queries or replies. So don't get too surprised if this value is there. You have a 40 gig link. The value seems to be rather high for a 40 gig link, and it doesn't go down over time. You should actually be happy, because if you have a stable network, this value will not be updated. So this is actually okay. The retransmit timeout, that's just a value that tells us how much to wait before we resend a reliable packet to the neighbor before it gets acknowledged. If we send a reliable packet to the neighbor, we need to wait till the acknowledgement comes back. If it doesn't in this time, we'll send the packet back. Queue count is the most troubleshooting useful column from here. Anytime we send a reliable packet out an interface, we also put that packet on a per neighbor queue. And we wait till the neighbor acknowledges that packet. If the neighbor does not, we keep that packet on the queue. In a stable network, these values have to be at 0, because whatever I told to my neighbor has to be acknowledged. During network convergence, it's possible that we will see non-zero values here, but if the network is stable and you still see non-zero value in the queue count, something is wrong. You have problems communicating your information to the neighbor. This will have to be somehow corrected. Finally, the last column, sequence number, just tells you the sequence number of the last reliable packet that you got from that neighbor. If your network is stable, this number doesn't have a reason to rise. There is no reason for this number to increase. So if you believe, again, that you have a stable network, that there's nothing going on in there, and still this number actually keeps coming up and increasing, you better check EIGRP, either the event logs or perhaps packet captures, to see what is being communicated between you and that neighbor, because you expect nothing to be sent, right? So let us see what can really go wrong here with the adjacencies. The adjacencies cannot be held up stably. They will continue flapping because we send information to the neighbor. It will not get acknowledged or not even received.
and the neighbor eventually drop the session only for that session to come back again. If you have a recent iOS, the message about the neighbor going down and coming back will also be accompanied by a reason code that tells you why the neighbor's adjacency has gone down. And these are the most typical possibilities. Peer graceful restart. Technically, this means that you have received a packet from the neighbor that has the init and restart flags set. This can be seen often when you change the configuration on the neighbor, such as changing summarization or split horizon. Also, if you have non-stop forwarding and that guy has just reloaded, this would be the same information, right? This means that it's not your problem that the adjacency had gone down, it's the neighbor's problem. You need to investigate that neighbor. The second option is peer restarted. Seems almost similar, but this is a hard restart of the neighbor. It means that the process on that neighbor has started over. We have received a packet from the neighbor that has just the init flag set, saying I'm starting over, but not the restart flag, which is used for graceful restarts. Again, the neighbor has to be inspected to understand what was going wrong over there, because it's not our problem, it's the neighbor's problem here. Holding time expired, I don't think this needs any comments. Retry limit exceeded, well, this is the unpleasant condition when we try to communicate information to the neighbor and he just does not acknowledge it. And finally, you can see information about interface peer termination received, sometimes called also interface goodbye received. It will be in the older iOS versions, the goodbye message. This tells you that the neighbor knew it's going down and told you about it, so that you don't wait for the whole timer to expire, but rather fail over immediately. Again, that's something to be checked on the neighbor. Why decided to go down? Typically, an interface shutdown, a configuration change. When you change the stub, for example, this is about what's going to happen. So let's see about the possible issues. The first possible issue, and the easiest one to also know, and also the easiest one to troubleshoot, is mismatched configuration parameters. Typically, the symptom would be that the two neighbors won't come up at all. Sometimes you may get a logging message, but typically those two neighbors just remain silent and are not there. What to check? Aside from the typical configuration parameters, be careful about ACLs if you happen to use them between routers, and also keep in mind that we need both unicast and multicast to be enabled in those ACLs. One nasty thing that can happen is the use of secondary IP addresses. If somebody wanted to play a bad prank on you, he would configure two networks on the router, let's say A, primary network 10.1.1, secondary network 10.1.2, and then configure the same networks on the second router but flipped. The primary would be 10.1.2 and the secondary would be 10.1.1. If you do ping tests, it will work. If you ping even the multicast IP address, it will work because the neighbor gets your packets and they are both on the directly connected networks. But EIGRP always establishes adjacencies using primary IP addresses only. So it will keep barking at you that the neighbors are not on the common subnet. A very useful thing here, if you just can't get the neighbor up, check the show IP EIGRP interface. You should see the interface there to the neighbor. If it's not there, well, check if it's under the network command and check if it's not passive. These interfaces won't show up there. It's a useful thing. And finally, check the unicast connectivity and multicast connectivity. We might not be that used to pinging the EIGRP multicast address, but this is again a useful thing because it tells you if the neighbor is actually listening to your multicast packets that could be also from EIGRP. You will get back a response to this multicast ping if the neighbor can hear you. The second, more involved possible problem is that your connectivity to the neighbor between yourself and the neighbor has broken connectivity in terms of unicast or multicast. Unicast works, multicast doesn't, or vice versa. Typically, this results in either one of the neighbors or two neighbors flapping. If you can hear the neighbor's hellos, you can create a neighbor table entry for him. But if you cannot exchange unicast packets, you won't be able to get past the initial synchronization. And if you don't get hello packets from the neighbor, you won't have him in the neighbor table, and you won't accept any packets from him whatsoever. Typical symptoms will then include also that if you do show IP EIGRP neighbor detail, you will see that the neighbor will be claiming waiting for init or waiting for init egg. And even down there, you will have the init sequenced information. This all is the information that we cannot get past the initial configuration and synchronization stage. How this could have happened? What could have gone wrong? ACLs are the typical culprit. Once again, be mindful of both unicast and multicast connectivity. Also be mindful of NAT. Now, this might be a little contrived scenario, but imagine that you have NAT, you are running EIGRP on the outside interface, maybe just to learn a default route, and you still have a static one-to-one NAT of that outside interface's IP address to some internal neighbor. Well, what that means is that when your EIGRP neighbor sends you a unicast packet, it will translate the destination of that packet to that internal neighbor, and you as a router will never process it. This is a nasty one to troubleshoot. Be mindful of this one. Once again, the pings are your friends here. Try pinging the neighbor unicast. If it doesn't work, check if you see the ARP entry for the guy. If the ARP entry is there, we have IP connectivity issues. If the ARP entry is not there, well, try to configure it statically and ping again. Because you might be running, especially in DCs like OTV or VXLAN, that play tricks on you with ARP and with broadcasts, and they may be having issues just with the neighbor resolution rather than IP connectivity. If even afterwards, with the static ARP entry, the connectivity isn't there, we have a basic L2 problem that has to be troubleshot. With multicast, again, this is a whole area. If I can't ping the neighbor's multicast group in which it listens for EIGRP, we are looking essentially at problems with link local multicast delivery. Again, be mindful that if you have non-Cisco switches there, they might play bad tricks on you with IGMP snooping and similar stuff. They may be actually blocking all multicasts if not IGMP is being received. So once again, this is about local multicast, points that way. Finally, these issues typically become noticeable in stretched L2 environments like OTV or VXLAN. That's what we see sometimes in the DC switching tag. Hands up, who is using EIGRP over VPC? Okay, let me devote 3 slides to this technology. You probably know that VPC allows me to create a port channel that goes to 2 physically independent devices. They will be called VPC peers. They need to be connected together with a link we call a peer link. That one is used for both state synchronization between the 2 Nexus switches, the peers here, and also carries normal traffic. Now, we need to prevent framed application and possible switching loops, and we do it by a very simple rule that says, if a frame comes in through a VPC peer link, it cannot go out through any physical port of any virtual port channel, because it might get down to the very same box that sent the frame in the first place. What is not that obvious is that we impose this rule also for routed packets. What I have in mind. Assume that we have the guy at the bottom sending a packet to the switch at the top with the IP address of 2222, and it's configured so that the default gateway is switch A on the left side. Switch A has a MAC address of X, so the router at the bottom will create a frame whose destination is X, insert the packet for 2222 inside, and let it fly. But because of the hashing, it lands on the physical link to switch B. Well, no big issue here so far. Switch B will simply forward the frame to its rightful owner, to switch A. However, switch A now knows, well, this frame came in from a peer link. I cannot send it up through another virtual port channel. This is prohibited. It doesn't matter that the packet inside would have been routed. So this doesn't work. To solve this problem, we have a feature that is called the peer gateway on Nexus switches. And what it does is, essentially, that we have those two switches share their MAC addresses mutually. Both switch A and switch B will listen to both MAC address X of the switch A and MAC address Y of the switch B, and they will act on it. So now when the frame comes, it's going to be the switch B that's going to route the frame, or actually the packet, and set it up. So we have solved this problem. All good.
Or not.
What's going to happen here, now assume that the router down there wants to talk in EIGRP to switch A. Let's say we're sending this null update, and this null update again lands on the link to switch B. Well, now the switch B listens to both MAC addresses X and Y of the two VPC peers, so it's going to consume that frame saying, oh, it's mine. Going to look into the packet, and we'll see the IP packet isn't for me. By my IP routing information, I need to route it. I need to forward it by routing rules, right? So I expect this to happen. Well, that won't happen because we need to decrement the TTL whenever routing. And when we do that, well, IGPs like OSPF, EIGRP, they used to send their packet with a TTL of 1, meaning that the packet will die on switch B and never make it to switch A. If you have a generic TTL security mechanism sending packets with a TTL of 255, that one will trigger again. The packet will make it through, but the TTL will go down to 254, and the GTS will not be happy. The solution here is to use a feature, again, we call layer 3 peer router, that essentially prevents the TTL from being decremented if the packets are being routed and forwarded across the peer link. This will essentially save you, but this feature hasn't been there available for all the time. You need quite a recent NXOS and suitable line cards. And now comes the jewel. If you have been running older iOS before 15.2, those iOSs have been sending their EIGRP packets with a TTL of 2, not 1. So even if you have been using your VPC and EIGRP without any of this layer 3 stuff, it just worked because EIGRP sent its packets with a TTL just high enough for the packet to make it to switch A. Well, since the upgrade, we don't do that anymore, and the packets will die. And this has been not really documented anywhere. We did a poor job here. So be careful about this. Finalizing the possible issues with adjacencies, just the unsorted possibilities. What else can go wrong? Never try to use a combination of static and dynamic neighbors on an interface. This is not supported in EIGRP. The moment you define the first static neighbor, you'll deactivate the multicast on that interface for EIGRP, so that's not going to happen. Either all neighbors are static or none of them are. Another possibility is a unidirectional link, which is essentially a layer 2 issue. Yet another possibility, again, a very bad prank played on you possibly, a hold timer shorter than the hello timer. This is particularly nasty because EIGRP adjacency comes up just okay, and when it's all is stable, then this goes down. And finally, all those non-EIGRP issues like packet losses, control plane policing kicking in, errors, this is something that has to always to be into account. Questions? Yes, please. The question is whether I need to use both peer gateway and the layer 3 peer router in the configuration. They both would go into the VPC domain section, and the layer 3 peer router makes sense only if you have peer gateway configured. Otherwise no. Thank you. Any other questions? Yes, sir. The question was whether there will be any adjacency issues if there is an MTU mismatch. In short, they will come up because they don't advertise their MTU, but the synchronization later can fail. And actually, this is something I'm going to cover right now.
because that's when the large packets come in. Okay, so let's see what can go wrong with the initial exchange of information after the neighbors have come up. Once the adjacency is up formally, we will try to exchange this whole set of routes in our topology tables. Be mindful that we use split horizon with Poisson reverse. So if I get a route from you and you become my next hop, I'm going to send the route back to you with an infinite metric. So that means I will make my update packets quite large. If there are MTU issues, we might be having trouble communicating those large packets between ourselves. Size of the topology table also matters. The larger it is, the more packets you will need to use, and the larger those packets will be. Again, pointing back to the possible MTU issue that will need to be resolved if there is any. So, the MTU issues will typically be seen by the inability for the neighbors to end up in a stable state. They will be up, but if you do a show IP EIGRP neighbors, you can expect the queue count to remain at a non-zero value again. The details won't tell you anything more about waiting for init or waiting for init-egg. That's not going to be there, but you see a packet enqueued and waiting for being acknowledged, which is never going to happen.
This would be the typical symptom of an MTU issue. Eventually, the neighbor will flap with retry, limit exceeded, come back, and the whole process will repeat itself, never-endingly. Another issue that can come into the play when doing the initial synchronization, well, be mindful of the fact that EIGRP is allowed to consume up to 50% of the bandwidth on the interface. Always make sure that the interface has a realistic bandwidth setting, hands off the bandwidth, in short. Keep it realistic and hands off. Especially be mindful of the fact that on older IOSs, the tunnel interfaces use a bandwidth of just 9 kilobits, which was very, very small, very slow. Obviously, since we also have the large amount of information on large EIGRP tables here, we can also be hit by packet losses, congestion, control plane policing issues, or physical layer errors. But the MTU issues here are by far the most common ones because the elementary connectivity problem would have been already dealt with at the beginning where we just established the adjacency in the first place. Once we exchange the routes, we want to select the best paths, have them put into the routing table, and then send to my neighbors. But because the best path selection algorithm is one of the poorly understood mechanisms in EIGRP, I would like to talk a little about it. And what I would like to do is go through the admittedly awkward terminology in EIGRP that still needs to be kind of mastered for us to look at the outputs properly. So let's start with the terms that you already know. Reported distance, this is something that you know very well. It's the distance of my neighbor told to me. Remember, there will be as many distances, as many neighbors I have for a particular destination, and each one will report the one to me. Now, the second value is what we call the computed distance. The computed distance is going to be a value that tells my total distance from myself through a neighbor if I also take into account the cost of the link between myself and the neighbor. And this is what we will going to eventually put into the routing table. So in this particular topology, if I'm looking at the path from A to E, the computed distance would be 20 through B, 25 through C, and if I'm not mistaken, 45 through D, because I'm just going to sum up all those values. And then we have the venerable feasible distance. This is one of the most poorly understood things in EIGRP. It's being often said that this is the smallest distance, current smallest distance to the destination. Well, it's not. Feasible distance is a historical record of how close I have been to the destination since the last time my road to the destination became passive. It's not necessarily the momentary best distance, it can also be lower. It's essentially, it's a historical minimum. We need it to act like this, but it also means that its behavior is dependent on time and on the way the network evolved.
During a passive state, the feasible distance can only go down, it can never increase. So it's just taking this as an example. If we assume that this was a network that just started, the best path from A to E would be through B. It's for $20, so let's make the feasible distance also at a value of 20. If the cost of the link between A and B went up from 10 to 15, the computed distance would change to 25. But since we did not need to go active, feasible distance would remain at 20. And now you have a difference between those two values. If that link later went down its cost to 8, well, the current distance would go down from 25 to 18. And since this is the new best distance we ever had to the destination, we would also update the feasible distance down to 18. And by the way, I don't have it here. If that link went back to the original cost of 10, I would be back at the situation I was at the beginning, the distance of 20, but the feasible distance would remain at 18. So that's why I said it depends on how the history looks like. The only way for the feasible distance to increase is to go active and ask your neighbors. That's the only way we can increase the feasible distance. So, the question was whether this implies the default key values or whether the k values actually have any meaning on this. No, this is an elementary way of how feasible distance works regardless of k values. And what we would be putting into the feasible distance is the resulting value from the formula, regardless of how those k values work and look like. We use the feasible distance in a condition we call the feasibility condition. This is a rule that tells us if we can use a neighbor because we can be certain it's loop-free or not. And you know the way it's being put. If the neighbor's reported distance is strictly smaller than my feasible distance, it's loop-free. Well, I don't know about you, I cannot remember this. I always have to somehow practice this. Let me tell you a more palatable way of putting the feasibility condition. If you are closer to the destination than I have ever been, you cannot be on a routing loop that closes through me. And why is that the case? You know, when something happened and I learned about the topology change, I know about it. Do you know about it? I have no guarantee that you do. I have the information, but just by looking at the metric, I cannot tell. And I cannot just grab a neighbor that provides the new lowest metric. Well, if I just lost my next hop totally, my distance is infinity. Anybody of you is better than infinity, even if I have been your next hop. So if I start routing through you, you're going to send the packet back to me. That doesn't help. I cannot be looking at the momentary distances. But if I remember that I never ever sold the ride to the destination for less than $100, and that guy, last information is that currently, well, the last information was that he sells the ride for $80, not 100. My $100 cannot possibly fit into his 80. He could never possibly have gone through me because never in my history I went through for less than 100, and that guy has 80. So he wasn't going through me before even I learned about the topology change. That less he is going to route through me if he learns that I have a problem. That's why the feasibility condition works. And that's why we need the historical data, the historical minimum in the feasibility distance. Successors and feasible successors, you know the drill. Just 2 words here. Successor has to be a neighbor that is loop-free, so has to pass the feasibility condition and provides the shortest path that is available. Feasible successor has to be loop-free, so again, it has to pass the feasibility condition, but does not need to provide the least cost path. In this topology, B would be the successor, C would be the feasible successor, and D would be nothing because, well, it doesn't pass. Normal situation, that's not a problem. Regarding D, well, based on its distance of 30, we cannot tell if it's going to send the packets back to me, to A, or if it's going down the direct route. We know by looking at the topology that it's not going to send the packets back to me, but we're not taking chances, right? So that's why the feasibility condition is called a sufficient condition. It tells me that he's loop-free, but if it's not met, he can still be loop-free, but we're not taking chances. Now I have a question for you again. I've slightly made a change in the metrics here. Now the link here has a cost of 1, and the link here is a cost of 20. So feasible distance currently would be 20 because this is the shortest path. B would be successor, C would be a feasible successor, and D is essentially nothing because it doesn't pass. Our best feasible distance, pardon me, is 20, and 20 is not strictly smaller than the distance of D, which is also 20, so D is nothing. But one thing to note here, D seems to be providing a shorter path, 21, than C, which is a feasible successor, 25. My question is now, what happens if B dies? Tell me. Any idea? What happens if B dies? C will be a successor. Yeah. And that's not what happens. Okay. This is the typical textbook cookie. If you have a feasible successor, you're gonna use it, right? This is what textbooks tell you. But notice, D, objectively, D is loop-free. D doesn't send packet back to us. Why should it? It just, the feasibility condition kicks it out. But we know that this seems to be providing a shorter path than C. We just can't use it because we are not absolutely certain. What's going to happen in reality is that, well, if we just use C, we would be on a loop-free path, but not on the shortest path that is available, and we don't want that. So, long story short, we're gonna go and become active. We are going to become active because we know that the neighbor providing the least distance is not a feasible successor, and we want to test if that neighbor is actually loop-free. So we're going to send out a query that contains our momentary distance through the failed neighbor, which happens to be B and happens to be infinity. Both C and D are going to receive that query, and since neither C nor D actually go through us, through A, they don't care. They just say, well, C will say, I'm still through 410. D is gonna say, I'm still through 20. And at this stage, A can simply reset the feasibility distance and pick D as the new successor. Router C has been and has remained a feasible successor only. This can be slightly confusing, and I can see you already having questions. So when exactly do we use the feasible successor? What's the rule, actually? How to summarize this? Let me try that. Whenever you learn about the topology change, the first thing you do, you update your topology table and compute the new distances. Then you search for the topology table, the whole one, and point to the neighbor that provides the least distance. You identify the neighbor. At this stage, you don't care if it's a feasible successor or not. You just identify it. And once you have identified it, then you ask, does he pass the feasibility condition? If yes, use it, golden. If not, go active. Because you don't want to miss the opportunity to use a shorter path if available. Right? This is what happens. Just because a neighbor is a feasible successor doesn't mean it's always going to be used. It might be used if we're thinking about fast reroute, but in normal EIGRP mechanism, we need to test. We need to go and test if the neighbor that provides the least distance could be used. This having said, let's look at the topology table and the data that's there because it's going to be using all the terminology we've just been gone through. Topology table is your best friend in EIGRP.
It's the EIGRP's playground. All that's happening in EIGRP, best path selection and dissemination, is going to be there. If a route is not there, you cannot tell it to your neighbor, you cannot install it into the routing table. So this is definitely a very good thing to look at. Show IP EIGRP summary topology summary, is going to tell you a summary information about the topology table, including the number of routes, including the number of replies that you have to send if you are an active router, and the number of dummies in your network, which I hope there are none. No, not really. This is just an internal data structure that is used to maintain the topology table, and this is not relevant information for us. Also, the list of so-called quiescent interfaces is a list of those interfaces that do not need to send or receive any kind of reliable packet. Could be good to understand which interfaces are involved in some kind of processing in EIGRP. The typical output of show IP EIGRP topology without the summary is like here, and taking the network at the right side of the topology into account, what we can see here is the list of successors, always will be listed first, and then the list of feasible successors, always listed at the end of this list here. Notice there is just a single feasible distance, not one per neighbor. And then we have information about the metric through the neighbors. We have the information about successor, feasible successor, if there is any. The number in those brackets after the slash is the reported distance, the neighbor's distance. And before the slash, this is the computed distance. The comparisons for the feasibility condition are always done between the feasible distance here and the number after the slash. This is what we check when we select the loop-free path. You know that if we add the all links keyword, we should be seeing all neighbors, not just the successors and feasible successors. There will be no big change here. We will just include the D as the, what we call for the purposes here, the possible successor. But otherwise, the format of the information is the same. I've got a question. Sometimes you wouldn't see all neighbors, even if you do all links. Why? Not qualified, not advertised. We are getting there. That will be probably about equal cost multipaths, but regarding the topology table, we can have many. Quick answer, split horizon, right? If your neighbor doesn't tell you the network, or if it advertises it back to you as an unreachable, you just drop it from the topology table immediately. Don't get scared if you don't see all your neighbors for a particular route. Those that are using you as their next hop, if they run split horizon, they won't show up. That's okay, that's normal. Finally, I'm sure you know this output, the verbose output here that calls out all the components of the metric we use in EIGRP to compute the overall metric. I'm not going to show it here because I will be using it later in the slides, but I'm sure you know it. Just a quick question. You know, for me, it has been kind of a problem to remember the components, the bandwidth, bandwidth, delay, reliability, load, MTU. Do you have any help to remember those 5 as they come one after another? At least for the distribution, it's useful to know them. Well, somebody came back and told me, you can use this sentence, big dogs really like me. Bandwidth, delay, reliability, load, MTU, like, okay, might be useful. Finally, sometimes it may happen that you cannot install an EIGRP learned route into the routing table because the routing table already contains a better path, better in terms of administrative distance. In that case, your show IP EIGRP topology will include an information that the feasible distance is infinite, and you will see that despite of the number of real successors, we will claim that the number of successors is 0 here. These routes are called zero successor routes, and if you want to focus just on those, you can use the zero-successors keyword in the show IP EIGRP topology command. This typically happens if you have either BGP or static routing also running on the router, and they compete for the same network to be installed into the routing table. Important thing about zero successor routes, they will not be advertised further in EIGRP. Your neighbors will not learn about these networks from you because you cannot use them, so you cannot guarantee their loop freedom. So we don't advertise them. Now, again, we have the symptom. We want a EIGRP learned route to be in my routing table, but it's not there. What to look for? First thing, always the first thing, assuming that you have neighborship with the assumed next hop, check the topology table. Check if that route is in the topology table and make sure it's also learned from that neighbor you expected it to be from. If not, consider all the things that can impact the advertisement of this route. You can have inbound distribute list, check that one. Or the neighbor may have outbound distribute list, so check it as well. There might be split horizon playing tricks on you. You know that in DMVPN phase 2 deployments, you need to deactivate split horizon on the tunnel interfaces. That might be the issue. Be careful about routes that already have a very high metric when injected into EIGRP, because as they progress further, their metric just increases. At some point, they may hit the infinite metric, and so they will be undistinguishable from split horizon, right? They won't be installed in the routing table. Be careful about too high metrics in your network. Also, EIGRP advertises what we call a hop count. This is just a remnant of times past when we try to prevent routing loops also by the typical means of counting hops. By default, this number is set to 100. And if the route is advertised more than 100 hops from its source, we will again just ignore it. We will not install in the routing table. It's a kind of a niche problem, but still could be relevant. The more niche problems, the more obscure to troubleshoot. And there might be an issue that you and the advertising router may have the same router IDs. This is again an obscure issue, typically done when you replace a router with a different one and leave the original one running without reloading it. Just gets a different IP address. It may keep its original router ID and advertise the routes with its own router IDs, and you will drop them because you have the same one. If you see that route in your topology table, but it's still not getting into the routing table, check whether it is reported with having a non-infinite feasibility stance, because it could be a zero successor route. Check what neighbors are satisfying the feasibility condition just to check that they are the ones you expect to be the next hops. And if you're using a recent iOS, you know that you're running what we call wide metrics. Regarding the wide metrics, we compute a very large number, and we need to downscale it when we install the route into the routing table, because routing table still uses 32-bit metrics. If that number produced by EIGRP is still too large, it will not make it into the routing table because it appears to be infinite. Make sure that the computed metric after the RIP scaling, which you see in the show IP EIGRP topology, is smaller than 2 to the power of 32 minus 1. Questions? None. Okay. Let's go forward. Let's check the problems that are possibly seen with advertising and convergence issues. In EIGRP, the convergence, having already gone through the feasible successor and successors, essentially there are 3 scenarios to consider. Your successor dies, and the feasible successor is there and provides the least cost path. That's the perfect thing. Second possible problem is your successor dies or becomes too costly, and the feasible successor isn't there at all or doesn't provide the least path available. So that's when you need to go active. And sometimes when the logic just defies understanding, and this is something goes very wrong, so it doesn't follow any rules. Here, you really need to understand your topology. You need to understand what's going on and how your network is actually supposed to look like when you lose a neighbor, to understand what's the supposed next behavior. Assuming in this network here, we're going to lose my successor B, assuming that we still have the router C, which happens to be the feasible successor, how would the convergence look here? Well, first of all, I need to say that the router C here will be the feasible successor based on the feasibility condition. And if I need to go just to replace the successor with the feasible successor, this is going to be a very short time. What would I see in the logs? Let's assume that the link from B to D to E dies. If I did the show IP EIGRP event log, this is what I would see, but we need to read it from bottom to up. At the moment B has gone down, or B's connection has gone down, B would send a query because it lost its only path to the destination. What I would see here is received query. I would see an information about trying to find the feasible successor, and I would see an information FC said feasible condition satisfied, saying, okay, I found a feasible successor providing the least cost distance, I'm going with it. There will be no query here, no information about going active, just information about replacing the next hop in the routing table. And if you had more time, just to see through those timestamps, this would take about 35 milliseconds, I believe. This would be a very, very quick operation. Very quick operation, actually, yeah. This is how the local computation would look like. You lose your successor, but your feasible successor is there and provides the least cost path. It's very quick and very simple. Let's see what we can do else. If we don't have C as the feasible successor here, which I'm going to delete in a moment, and again assume that I'm going to lose B as my successor, how does the process look again? My topology table would again look like this, and I'm pulling out all links to make sure that I am seeing all possibilities. And well, A is the successor, B is the successor, C is the feasible successor here, D is nothing currently. What I'm going to do to make this failure here, I'm going first to simply drop the link to C to lose the feasible successor and stay just with B and D being nobody. And then the link from B to D is going to die. Again, what can I expect to see in the event logs? Those event logs will tell me, first of all, they're trying to find a feasible successor, just like before. But I will find out that the neighbor providing the least distance after the topology change isn't a feasible successor. So there will be an information saying feasible condition not satisfied. And then there will be this dreaded word active. This is the time when we start sending out queries, awaiting replies to come back, all replies to come back, and then we can do the path selection again, which starts again in the section of find FS. This would appear when we get all the responses we were waiting for and make our choice again. The time necessary for this proceeding would be larger, depending on how many routers you needed to ask and how deep the query needed to go. This is how it looked like for a diffusing computation. Please, hands up, who has been hit in the past with stuck inactives? Yeah, this is a problem in EIGRP that's there because of its design, and it's very difficult to do. You know, what's at the core of the stuck inactive is that how the diffusing computation works and how the query is propagated on this just a very, contrived topology. If you need to ask, if you need to send out a query, there's a couple of principles you need to follow. When you send out a query, you cannot close the diffusing computation till you get back all the responses. Now it depends on who was queried. If he can reply immediately because he doesn't care, your problem is not his problem because he uses a different path. So assuming that the neighbor at the right isn't having any problem with your increased distance, it's just going to respond with its own current distance. If the routers below and above, the router in the middle, have been using you as their next hop, they might get affected. And if they get affected so hard that they need to ask further, the diffusing computation just expands. You cannot send back a response. You cannot send back a reply until you have received all the replies you wait for yourself. So we are waiting for the query to hit either the edge of the network or some router that is not being affected. So we wait for the replies to come back. Only then those routers can stop being active and send back their own replies. And only when they send back their replies, I, as the initiator of this diffusing computation, can stop being active myself and do the best path selection. See, this diffusing computation creates a chain of interdependent routers that depend on themselves, and any single router can then become dependent on each other. What can limit the depth of query propagation? Well, we can use router filtering, distribute lists. What they do is they prevent routes from being advertised further. They do not impact the query itself, but if a query comes to a router that doesn't know anything about the route, it's just going to respond back again immediately saying, I don't know nothing. I know nothing. Infinity. The same thing happens with summarization. If you are using summarization, again, summarization will not affect the query itself, but if the query crosses the summarization boundary, it will not know about the components of the summary and will respond immediately, I don't know. It's a very powerful tool. And obviously, you can have neighbors that are stub, or you may have no neighbors at all, so you just respond back. These all are things that limit the query range. The smaller it is, the smaller the chance of getting stuck inactive. So, once again, the diffusing computation creates a chain of interdependent routers. And if single one is misbehaving, well, that can prevent that computation from ever finishing. This is the Achilles heel of EIGRP. This is one of the things how we make, the coordinated updates. They are the way we make it loop-free. But also, if something's misbehaving, this is also where we kind of perish. And the state where we cannot conclude the computation is the stuck inactive state. There are two major things to consider in stuck inactive. A route has gone active in the first place and has stuck in there. Both reasons need to be investigated when that happens. Why it has gone active and why it has stuck there. Event logs will be typically the ones you will be looking into because they're very useful to understand who have you been querying and who was waiting for a reply which never came back. Troubleshooting this will always need us to look why the route went active. Well, this is easy to find out. Typically, why it was active, you will see that in the event logs. Why it became stuck inactive, that's a more difficult thing to do. With the active things, we will see that in the event logs. The event logs ourselves will tell us who asked us or what metric has been changed, where did the query come from. Troubleshooting where the replies stop getting back, this is the real problem. If you are currently in a state where you have a route in active state, you can check the show IP EIGRP topology active. This will tell you which routes are currently active. But you know, those routes will remain active for only 3 minutes or 6 minutes with the CRE write feature we have, and then we'll go down with the whole adjacency. So the problem in troubleshooting this is that we have a limited time to find out who is misbehaving. What can be done here? This is just a very simple and contrived scenario to show you how the process would look like if you had the time and you were right on matter when it was happening. So we know that there is an active route on A because one route on router A just died. What you would see in show IP EIGRP topology is that the route would be active. You would also see that it's waiting for a response from router B. This R tells us that we're waiting for a reply. Since we're not getting back a reply from router B, let's check what B thinks about the whole situation. I'm sorry, I went too far. Why B hasn't replied? Well, B is waiting the same way for router C. Again, we see that router B is waiting for the neighbor reply to come back. Checking C. What's C's problem? C would see that okay, this is a slightly different output here. What we can see here is a number of retries that we have already tried to resend a query to the neighbor, immediately suggesting some communication problem. And we see that both router C is waiting for D, that's the R flag waiting, and the S flag would mean also that we already send a SIA query to the neighbor, asking, are you really working on my query or what? Or is it? Let's go and check. Check its topology table, cool as a breeze. Would love that, but this is not helping. It says there is no active route here. I mean, so a moment. If there's no route active here, why is C still being active? Let's check it and see. Checking C, oh, it's still there. It's still waiting. We do have a communication problem here, obviously, because D doesn't even understand it has been queried. So let's try to ping it, We see that the Q count is non-zero. Trying to ping it, it's dead. And this is essentially when this contrived scenario ends, because then we will be going into troubleshooting why we cannot even ping D, why it has been up, and so on. This just shows you how the typical process used to look like when you had the problem there, right there, and we're going router after router after router to find out where is this problem staying. Sometimes you would be even chasing routers in a circle. There is an improvement that came around to year 2000 where we would extend the code with a feature that allowed the neighbor to ask, did you get my query? That was the SIA query question, and the neighbor would reply, yes, I'm still working on it. That's the SIA reply. That feature allowed us to move the breakup of the adjacency because of the missing reply closer to the router where the problem is happening. Still not perfect, but given the nature, it's likely the best we can do for the moment. There is also another possibly good thing that you might want to turn on in your network. It's called the soft SIA feature. This allows you to not to drop the adjacency totally to the neighbor which isn't responding, just resynchronize, meaning that those routes that have not been affected will not go down and back up. They will stay there. It's like a graceful restart. It's useful. What can provoke SIAs? Stuck inactives. Better congested links, kind of obvious. Second thing, MTU issues. Again, especially if you had a topology change that included lots of networks and you need to ask about lots of networks in your query package because they will be long. Short queries will make it through. Large may not. That's when the MTU issue is going to hit you. Another issue, query is too deep. You have too large a network without summarization, without filtering. And the query just needs to go very, very far. And with all the processing delays, possibly packet drops and so on, you just run out of time. Excessive redundancy. This is something that has bitten people hard. 2 distribution switches, 100 VLANs, 100 SVIs on each of them, and 100 EIGRP adjacencies because in a good intent, you included all those networks in EIGRP. It's not helpful, really, because those VLANs are likely going through the same physical infrastructure, so there is a fade sharing. If the physical link goes down, all VLANs go down. There is no added redundancy. Make those SVIs passive. You will significantly decrease the load that those 2 distribution switches have when they do any kind of EIGRP talk between themselves. Obviously, overloaded router, overloaded CPU, or cup drops. Sometimes we have seen, especially in iOS, problems with memory. iOS doesn't have virtual memory and cannot defragment memory. So after a long uptime, what may happen is that you do have memory, but not in a single contiguous chunk. You get a query, you need memory, but you can't get enough of it to construct a reply, so the reply never comes back. A reload is unfortunately, the only solution here. And software defects, obviously, coming in. Yes, sir?
Going back to the example you had,
yes.
C was still waiting on the reply from D.
Right.
So in that example, they lose connectivity. So when a router is waiting for a reply from a neighbor that it goes down, like what happens once that adjacency is down?
We pretend that we received an infinite response from the neighbor. That's all. We terminated there. How to minimize the possibility? Summarize, summarize, summarize. Whenever possible, this is the most helpful and most useful thing in EIGRP to do. If you also can do filtering, please do that as well. If you can, use the EIGRP stub feature. Please do that as well. This is a wonderful improvement to EIGRP scalability. And possibly run an iOS, but I suppose you're really doing this, that includes this SIA query and SIA reply extension, which would be an iOS compiled anytime after 2000, which is, I suppose, what you're running. As an added bonus, to stabilize the network, even if you are possibly hit with SIAs, consider using the soft SIAs here. Yes, sir? Passive interfaces are also wonderful, but you know, this is a design issue. Can you afford having a passive interface to another router? Well, that's the thing. I can declare my stub networks. The networks that go just into end networks with just end host as passive. This is more like an efficiency and effectivity and security thing that I won't process EIGRP packets coming back to me and won't establish adjacencies if there are any possible routers. But there shouldn't be any in end networks. I had already this example with too excessive redundancy between distribution switches. But just by, you know, if I really have a network that doesn't go to any other router and declare it with a passive, this is not going to have any impact on the query. So this is not really something that will make a change. But thank you for the question. All right, so much for SIAs. Regarding the problems with summarization, this is more about the proper use of summarization rather than defects being seen with summaries. But since there can be issues happening with this, let me talk you a little about what can happen with summarization. In EIGRP, as you know, summarization will take a number of component routes and advertise a larger route that is replaces their whole scope, but is just one in instance. And regarding the metric of this summary route, it will inherit the cost of the cheapest component there is. When this is being done, it's been done for a good purpose. We want to, to advertise, the cheapest way to reach the whole range. But this also means that if we have a churn in the list of those component routes, we also need to recalculate and re-update that summary route anytime the component comes in or out and happens to be the cheapest one. From the perspective of the surrounding routers, this is not helpful. We advertise all the time the same summary, just the metric changes up, down. That's not helpful. What can we do here? In the named mode of EIGRP, we can actually state what should be the metric of the summary route we have configured somewhere else. The advantage for this is both for the router that performs the summarization, because it's not going to have CPU spikes every time you learn or lose a component, just to make sure that you advertise the best path. And also for the other routers, our neighbors, they won't see a thing, because suddenly that same summary will stop getting updated again and again, just with a new metric. This is done primarily to slow down the churn in your network and prevent the router that performs the summarization to do unnecessary CPU cycles for a metric update that doesn't really make any sense. Now, the more complex issues come if you have multi-homed remote site like the one here with C, with, let's say, headquarters routers A and B, and an internet access point which is up there and doesn't have a name. Assume that you want to send just a default route down to this multi-homed remote site C, while you are receiving that default route from the internet. What you would do is configure A and B with a rather lofty summarization. Everything goes to a default route. So the router C down will then learn just the default route and nothing else, and the default route will be an internal route. A and B are supposed to be receiving their own default route from internet. Will this work or not?
What are the problems here? Sorry? It's assumed that this would be an EIGRP peering. Yes, this would be an EIGRP peering. Well, you know that whenever we do summarization, we install a discard route, this route to null 0 in our routing table, and the administrative distance of that one is going to be 5 by default. So if we learn about a default route from EIGRP, either internal or external, that is going to be 90 or 170 by default, the summary route will beat it. So if we just summarize like this, A and B are not going to accept the default route from that internet router because their loop prevention default route will take over. Well, this is nothing new, really, and this could have been solved by stating an administrative distance in the IP summary address command, which would then look like shown there, and in that case, what will happen is that A and B will still learn the default route, but whatever they send down to C, they will summarize as a default route. So if this network is configured like this, and all links are up, all's good. Well, and let's assume that now the link from A goes down. What happens now? Router C learns 2 default routes. One is being learned from B, and that is internal, a result of the summarization. Router C, I'm sorry. B is getting the external route from B, yes. I'm sorry here. What's happening here? Since A has lost this connectivity here, it will advertise the remaining networks that it has on itself, summarized into default route. That will be internal. If this route from B is external, the one from A will beat it to it. And because we always prefer internals to externals, we will follow the path to A, which leads nowhere. How to solve this? There is a possibility that we can define the summary network with an administrative distance of 255. This is actually a very, very specific way of doing this. What will happen if you do a 255 on a summary metric is that you will only advertise that network if you happen to learn it yourself exactly as written, in this case, exactly the default route, but you won't advertise it if you don't learn it itself. If A learns the default route with this kind of summarization, it will pass it further. If it does not, it will not generate even the summary. It's not going to come down to C. So either A knows about the default route and that's when it sends it, or not. And this would be then the solution for this problem here. There is a note that don't use this for single homed locations. Any idea why this might be the case? Why this would actually make problems, this 255, if we had just a single home location? Once again, the question is, we have 255 as an administrative distance, but the C would not be a multi-home location, just a single, uplink. What could possibly go wrong here is that, remember, the default route here replaces also your connectivity to the rest of the company. And you may be not learning the default route, but you still want to read the rest of the company. If you do the administrative distance of 255, you will only send the default route to C if you get the default route yourself. Well, the default route may be gone, but the rest of the company isn't. And you don't want to lose the connectivity with that one. That's why we don't want to use the administrative distance of 255 with a single homed locations. Well, obviously, another solution would be just to use a plain good old filtering, so the distributed filters, and just to send down the default route. And if those routers A and B don't get any default route themselves, they have nothing to advertise,
So there will also be floating statics coming up here, pointing up those folks in case they do not have the default route, to still make up for the connectivity inside your company. These are more like the design issues, but still they can come back and bite you depending on how your routing is set up. A slightly more convoluted scenario for summarization is in this network. Again, assume that you have two routers A and B, which aggregate a couple of locations. And to make the routing simple, they aggregate those component networks here behind CD and E into a very simple summary 10.1/16. And they advertise it to router X that is somewhere up the hierarchy, up to the core. If all routers are up and running, and if all those component routes are up and running, this works perfectly. X may decide to send some packet through A and some packet through B because it learns the both summaries from both A and B, and they would probably have the same metric. This is all okay. But what happens if, say, A's link to location C dies? The summary that A is advertising doesn't change. So the router X still sees two paths, one through A, one through B, for the whole 10.1/16 range. And it may still decide to send the packets for location C through router A, because it doesn't know something has changed. Now A has no way of forwarding those packets because it doesn't have a link to B. What is the solution here? I've just betrayed it. We need a link to B. So one of the possible solutions for this design is to put a link, direct link between A and B and not have a summarization there. Have those two routers exchange the unsummarized routes to help them understand that they can reach the networks through themselves. And if adding this extra physical link isn't feasible, we have GRE tunnels. Maybe a slightly pathetic, but again, a very smart and flexible solution. And again, it's not here. Now it's here. It's still there. It can be used to exchange both routes and forward those packets which cannot make it from A because A has lost the connectivity. Truth be told, there has been an enhancement filed for EIGRP to exchange these types of information directly, but has not been implemented. Whether it's going to be implemented, I'm not sure. It has been quite old, without the help of extra tunnels. Questions about summaries? None. Okay, let's move forward. Trouble with redistribution. Well, this is a wonderful thing. Every time we are polluting one routing protocol with information from another, this can be nasty. In this scenario, let's assume that you have a router A running the most wonderful distance vector protocol before EIGRP, which is RIP, and we need to get the RIP path down to B in EIGRP. Okay, we do that. We do this redistribute RIP, think how well we've done it, check the B, and well, it's not there. What's gone wrong here? You tell me. Did not install RIP. Yeah, the redistribution metric. Keep in mind, EIGRP or any protocol for the matter uses its own way of computing its own metrics. There is no way of sensibly translating one protocol's metrics into another, and EIGRP is not going to invent those metrics for you. Okay, in some cases it will, but essentially, this might be actually a dangerous thing to do. When I said sometimes it will, these are the exceptions. If you redistribute connected networks, EIGRP will grab that interface and its metric. If you have static routes that point out physical interfaces, not through next hops, just through interfaces, and redistribute them, again, EIGRP is going to grab the metric of the outgoing interface and put it as the metric of the redistributed static route. If you redistribute between EIGRP processes, the metric will be just retaken 1-to-1 because this is the only compatible operation we can do. And in cases of MPLS L3 VPNs, what we do is if the original protocol at the other side of the VPN has been EIGRP, then we have tricks to save the original metrics in BGP attributes, carry them over, and reconstitute them back into EIGRP when we redistribute them back from BGP into EIGRP. Well, if you want to impress somebody else with how well you know these exceptions, please do. But mere mortals like me just configure the redistribution metric every single time. You can't be wrong there. Yes, sir? A static route that points to? Well, if I have a static route that points to an IP address, that is not going to be redistributed at all unless I specify the starting metric. The redistributed static will only work without this redistribution metric if the static route is like IP route something something tunnel 0 or serial 1/2. The moment it includes the next hop, EIGRP puts it in the way and says, you need to specify the metric. I'm not going to take it. Yeah. GRP? Yes, but we do this kind of shifting the metric by 256 and back. But you would need to run iOS older than 12.3 to have EIGRP. EIGRP hasn't been in iOS since 12.3 onwards. It's a very, very old thing. Sorry? Hopefully not. Hopefully not. Yes, sir. This doesn't matter. Technically, it can be anything because we transport the metrics as extended communities. Typically, inside a single AS VPN provider, it would be IBGP between the PEs, right? So the idea is that the PEC protocol would be EIGRP between the CE and PE on the MPLS L3 locations, and if you do the EIGRP to BGP redistribution on one PE, BGP will automatically grab those metrics, put them into extended communities, and when you transport those routes to the far end PE and do the backward distribution from BGP into EIGRP, those communities will be automatically, without you doing anything, used to reconstitute the original metric. Be very careful about doing lazy type of redistribution like here. This doesn't work well. The problem here is that you will end up with a very high starting metric, which doesn't have much room to grow as it goes across your network. So if you have costly links, you may really end up with this metric actually ending up in an infinite value somewhere halfway across where you need to get it. Always be certain that the redistribution metric is something reasonable. It doesn't matter what exactly it is, as long as you have just a single redistribution point, because you don't have an alternative, which one is better, right? But still make it kind of reasonable. The values that can be used here are typical for 1 gig link or 10 gig, well, this is 1 gig. 1 gig link, and they will work just nicely. Another more of a, let's say, surprise rather than a real problem is that you actually find yourself seeing a network in EIGRP that has not been included as a, that is a static route and suddenly makes its way into EIGRP and you didn't do any redistribution yourself. This is actually a feature that has been in iOS since ages, and is that if you define a static route, again, out an interface only, no next hop, just an interface. For certain purposes, this route behaves like a connected route. For example, if it was out an Ethernet interface, we would be doing ARPs for every single IP inside the range of that static route because we feel it's directly connected. EIGRP acts on this And if you have a network command that happens to cover that static route, which points just the interface, not the next hop, it's going to inject the network into EIGRP and transport it. Be mindful of this, because you might find yourself seeing those routes in your EIGRP even though you didn't redistribute them because they're static. It's a feature, it's not a bug, though the usability is kind of questionable. So this is how it would look like. Yeah, well, the show IP EIGRP topology would tell you that the route is actually coming from a static location. Finally, multi-point redistributions, do you know they are always prone to possible routing loops, and this typically happens if you happen to have a route that is already external in one of the two routing protocols, then you carry it over to the second one, where it will be external by design, and inject it back into the original one, and if you happen to inject it back into the original of the lower metric, then it originally had, you may end up having a permanent routing loop that will never go back. Solving this can be done in multiple purposes. One of the kind of more pathetic ones is not to do a multi-point redistribution, or at least not inject the routes back and forth. But obviously this is not a solution for most of the scenarios we need to solve. So the more appropriate ways of approaching that, well, yeah, it's a bad thing if you have a loop. We can do four things. Redistribute it either in one direction. As I said, this is not really likely a solution. We can filter the routes based on their prefix. We can filter them using route tags, or do some kind of tweaking of their administrative distance based on who is telling you the route, either router from the EIGRP world or the router from the OSP world in the previous example, because you know, based on the routes, what source they are supposed to be coming from. By far the most flexible approach is the third one, using the route tags. The idea is that when you take a route from OSPF and put it into EIGRP, you give it a tag. And when you redistribute it back from EIGRP back to OSPF, you check if it has that tag and drop it. Others will make it. The configuration is kind of typical here, and this is how it would technically look like. We take the route from EIGRP, have it in the OSP with a metric, say, with a tag of 1,000, and we won't allow it to go back into EIGRP if it already has the tag of 1,000. This is the general idea. Questions? Yes, sir. Imagine that the route is originally external in EIGRP. That might be the problem. Or for some reason, we don't distinguish between the external and internal routes. EIGRP does, so if it was external, that would be the risk. What other propagation problems we can actually expect in our networks? Zero successors are one of those which we absolutely, don't look typically for, but if they happen, we don't see the route being advertised to our neighbors. Once again, a zero successor route is a route that cannot be installed in my routing table because there is another one, the same as far as the destination goes, but is better in terms of administrative distance. It may be coming from BGP, it may be coming from a different routing protocol, it may be static. I will not advertise that route because I cannot guarantee it will be loop-free in the end. This is what happens. Typically this happens, when we have routing protocol overlap. But less obvious thing is that you might be, for some reason, running, let's say, 2 or more EIGRP processes. And by chance, again, they are there, and they try to install the same route, both of them, into the routing table. Again, one of them will fail. We'll have the zero successor route, and will not advertise the route further. Technically, it's possible to run multiple EIGRP processes on your device. You should, though, be mindful that essentially, if you have multiple processes, you want to have multiple domains. You want them to be separate. So having overlapping networks is something you should be mindful that might not be a good design. Depends on what you need to do. But in general, if you have 2 independent processes, you likely have them because you want to have them separated. So it's kind of strange to advertise the same route in both of them. This goes back to this design. Duplicate router IDs, they are a hideous thing. Do you know or do you have any idea about the router IDs in EIGRP and where we can actually see them and what have they been used for? Any idea about router ID in EIGRP? Newer iOS versions, it's going to be there. That's right, that's where I will see this EIGRP ID. And what was it used for actually? This EIGRP router ID. Back in originally, yes? That's right. It was originally slapped onto all redistributed networks, and the router ID would be the router performing that redistribution. In all times, it has been used as an additional means of preventing a possible routing loop. A router seeing a route, it has inserted itself. Since some advances in EIGRP, we have started tagging all routes, not just externals, but also internals with the router ID of the router that injects them first into EIGRP. This has not been made public too much in the beginnings. And again, if a router receives a route tagged with its own router ID, it's going to totally ignore it. It's not going to be logged in logs. It's just not going to be in the topology table as if it never arrived. You will see that in show IP EIGRP event, that the route has been ignored because of the matching router ID, but it's not going to be logged anywhere else. So it's kind of a silent thing. Be careful about that. We've seen situations, as I said before, where a device was kind of migrated to another device in terms of the function, although the original router remained there, was just renumbered, got a new IP address, and became, let's say, a standby or a secondary router. Because the addresses have been moved to the new one, those two routers ended up having their router ID the same and ignore themselves silently. Be mindful of this. Be mindful of this. The router ID is going to be displayed in show IP EIGRP topology in all ISs, show IP protocols in newer ones, and this is how it would look like if you were looking into the event log if you ever got a route that contains a duplicate router ID matching yours. By the way, the router ID in EIGRP is chosen just the way it's chosen for OSPF or any other protocol in iOS. By command, if not command, the highest IP between loopbacks, if not loopbacks, the highest IP from other remaining interfaces. Just like that. We do have a kind of a new, okay. Yeah, this is what it was first advertised. Finally, some of the specific EIGRP features to cover here. One of them is the, and this is old one, but still needs to be taken care of, the possibility of EIGRP pacing its packets. Once again, we allow the EIGRP to take up to 50% of the configured interface's bandwidth for its own packets if necessary. If not, the bandwidth is there for other traffic. I cannot emphasize this enough. The bandwidth setting should be to a realistic value that typically reflects on the real speed of the interface. On interfaces that do auto-negotiation, Ethernet like that, you don't need to touch it even because it's always going to be up to date. Serials, tunnels, they may need to update this to a realistic speed, but once again, don't put it too low because you will slow down the EIGRP. Don't put it too high because you may overload, because even 50% may overload the physical interface where the packets are going out. Be realistic. There's a point with this kind of EIGRP pacing on multi-point tunnel interfaces with DNVPN. What EIGRP does on all those NBMA, non-broadcast multi-access interfaces, is that it takes the bandwidth, divides it by the number of the neighbors you have on that interface, and allocates the fraction of the bandwidth to each of the neighbor. If you have lots of neighbors, you may want to consider not tweaking the bandwidth, because also the QoS policies may depend on that. You may consider tweaking the reserved percentage of EIGRP to allow it possibly more bandwidth when it needs to talk to those neighbors, especially in large DNVPN deployments, because you want your packets to go out eventually, not throttle them down. So rather than moving up the bandwidth setting, move the IP EIGRP reserved bandwidth. With DNVPN, the thing is always kind of complicated because the DNVPN has, this is what I already said. With the DNVPN, EIGRP thinks that the tunnel interface works in a multicast mode because this is what we present to EIGRP in the code. Unfortunately, the underlying connectivity for DNVPN is unicast. So we do a kind of lots of replication on the background for all those multicasts, and you consume lots of buffers for this. Physical interfaces for large DNVPN should be tuned to allow for large packet stores, to allow those replicated packets to be stored till they can be sent out, not get lost inside the router right now because you don't even have the buffer space. So think about queue limits in QoS policies. There are also certain commands I'm not including in this slide deck, but they will be available in the PDF, where to look for, where you are actually troubleshooting the DNVPN and EIGRP deployment, what outputs to look for the buffers, for the queues, because these would be the indications for EIGRP problems if they have been depleted. Once again, since we do the head-end replication for all multicasts and broadcasts in DNVPN on the router that terminates the tunnel, its buffers will be strained. So if there's a lot of EIGRP traffic, it's good to think about tuning those buffers on those interfaces to be able to hold all the traffic in EIGRP that's necessary. That's right. There's one specific feature that deserves a notion, and this is actually the last one I'm going to cover here: problems with links larger than 1 gig. You know, when EIGRP first came, fast Ethernet was considered fast. In order to simplify metric calculations, the bandwidth, as advertised in the original packets, has been carried in a form we call a scaled form. We took a constant of 10 million and divided by the bandwidth, and that was the value that we put into the packet. And each time the packet would be received by another EIGRP router, it would be converted back to bandwidth, then back to the scaled form and again. And because we do just an integer maths, round-off errors would eventually accumulate. Also, because the constant is 10 to the power of 7, 10 million, that was the maximum speed that we could actually differentiate in EIGRP, 10 gigabit. And that was it. For all faster interfaces, the bandwidth component doesn't make any change because we cannot put 0 there, but we cannot also do fractions, right? The fastest link in the old classic metrics is 10 gig. This is how it looked like on a Catalyst that was running a 20 gig port channel. Okay, it says the minimum bandwidth is kind of unrealistic, 0 kilobit, but you know, that doesn't really make sense. This is how it ends up with the classic metrics. The second metric we use is the delay. The delay is just a constant, which is an approximation of how long would it take to send a packet through an interface of a specific speed. This is something EIGRP doesn't even cover. This is hard-coded and hardwired in the iOS infrastructure, and EIGRP just pulls out the value. And again, those values have been suggested and tabulated for interfaces of certain speeds, and they don't change starting with 1 gigabit even, right? They won't change. So once again, based on the delay, we are unable to differentiate between the metrics, between the interfaces that are faster than 1 gigabit. So what will end up is suboptimal routing. Regarding the delay, well, it was always possible to configure it manually, but from an operations perspective, this is awkward. This forces you to go and tweak those configurations yourself. And as an example that explains everything, As you can see here, the left part here in this topology is 10 gig, the right part is 1 gig, but EIGRP with classic metrics is certainly going to choose just the right path simply because the sum of delays here is going to be smaller than the sum of delays here, where 3 links versus 2. Well, why did you then invest into 10 gig links in the first place, right? We want to differentiate between this, and that's why I'm going to apologize for just skipping this slide because it's just a segue. That's why we introduced what we call EIGRP wide metrics. They have been around for quite some time. Their idea is that we stopped scaling the bandwidth and we made them essentially to be 64-bit computations, allowing us to differentiate for both bandwidths and delay in a much more, scalable and granular way. If you wanted to know if you are actually running EIGRP with these wide metrics, you would be going to and checking the output of show EIGRP plugins. If it says that you have an EIGRP release 5 or more, you are running them. And also, if you do show IP protocols, and the K values you see there tell you something about K6, you're running wide metrics as well, because K6 comes with wide metrics. The wide metrics actually have 2 parts or 2 aspects to them. They will have 64-bit computations going inside the router's memory and logic, and they will have a new format of packets on the wire. Once the routers support this new packet format, they will always use it if they support it. If they don't, they will continue using the old one. The computations in the background can still be done in 64-bit precision or 32-bit precision. They will be 64-bit by default if you do the named mode, right? The moment you do the named mode, you get 64-bit computations. On a router that supports these wide metrics, but you do a classic mode, just router EIGRP1, you will get just 32-bit computation. If it is necessary ever to force the named mode to use the classic 32-bit computation, for whatever reason, you just suspect it's doing something wrong with your metrics, you can downscale it with this hidden command over there, metric version, either 32-bit or 64-bit. It's hidden, so you need to write it in its entirety. That will downscale the way it's going to do the computations. Not for use in stable production networks, obviously. This is a troubleshooting command to find out if the metrics may be at the core of your problems. Yeah, this is how it looked like if you actually looked into show IP EIGRP network for the new metric. You may see, okay, what is there? Picoseconds for the latency, which we didn't have before. We had milliseconds, microseconds. And also you will see that there is a added information, rib is and certain metric. This is the downscaled metric that is computed from the huge one by dividing it with a certain factor that can be also configured. By default, it's 128, and only then this metric is being put into the routing table. This is made to make the resulting metric somewhat shorter and more pleasant to look at when installed into the routing table. We do have certain issues with this that go back to the interoperability with the routers that implement the old, let's say, narrow metrics only. Well, first of all, we had certain issues with interoperation with iOS XR. This only involves problems in L3 VPNs. I'm not going to really dwell into the details. Let me just say that if an XR router was paired with an iOS router that was using the old metrics while the XR was doing the new metrics, was able to do the 64-bit computation, under circumstances, the XR could point to the iOS, and the iOS would be pointing back to the XR, and you would have a running loop. The workaround would be to force the XR itself to do the 32-bit computations only, and the command would have been metric version 32-bit, and in certain older versions of XR, you would need to do a test command at the beginning because it was implemented as just a debugging or testing command. And also, if you combine new and old metrics and do offset lists, you may know that if you do offset lists, the offset lists actually translate themselves into modifying the delay metric. The increment in the delay metric may be different between the old and the new, on the new version of metrics. They will likely do what you want. The metric will go high, but not by the same increment you actually specified. Don't be surprised. Don't be surprised. Okay, so let's wrap it up. We do have a number of nice tools in EIGRP to have it troubleshoot. We do have a number of tools that should help you to be very effective in isolating and nailing down the problems. Where to search for further help? Please be favorite of the Cisco support community and Cisco Learning Network. Those are two wonderful communities. We have designated VIPs there sitting over there that help those people a lot. Please come there because there is wonderful people there who can help you if you do have any kind of EIGRP problem. There is also a very nice list of documents on the CCO. These are all links. Lots of documents about troubleshooting different EIGRP problems, including the ones I have covered here. Hopefully, I have helped at least here as well. A couple of shameless advertisements. Well, these are wonderful books. Either the Design Solutions by Ivan Pepelniak or EIGRP for IP from Alvaro, Russ, and Don Slice. If you want to get nitty-gritty, you may go down the RFC road and read the RFC because you may know that EIGRP is now open. General reading about EIGRP and also other protocols include the wonderful books about IP routing, optimal routing design, Cisco Intelligent WANs, including the one I had my hands on. Leave it up to you to decide if it's good or not. What I would like to ask you, please be candid and do find your time to fill in the surveys for every single session you have been here, because this helps us to provide you with the sessions you need, and it helps us to come the next year.